Okay, so in this lesson we're going to introduce a couple of things. First, let's talk about atomic mass. So before we do that, we need to talk about isotopes. Isotopes, these are atoms that are of the same element but have different numbers of neutrons. So in this case, the way that we describe this, we have two different ways to sort of designate them, to label them. So the first one is the hyphen notation, and the second one is the nuclear symbol. Now, I'm going to kind of break these down. First of all, the hyphen notation talks about the element name, a hyphen, and then the mass number. All right, so the element name is not too hard. There's a hyphen in there for the hyphen notation, but the mass number, this is the one that we need to kind of outline again. So the mass number is going to be basically the sum of number of protons plus the number of neutrons in any single isotope or any single atom. So this is information that will be provided to you in some way, shape, or form. But of course, it's something that you can figure out based on some of the information provided. So let's go and see how this works. Over here on the right side, this chart right here, this isotope, this one really, I'm just really referring to the hyphen notation of these isotopes. So the hyphen notation, again, you see, right, you have hydrogen dash, with the hyphen, and then 1. What does that really tell us? Well, it tells us that we're talking about the element of hydrogen and that the mass number is equal to 1. So what information can I get from that? Well, for this one, right, looking at hydrogen 1, the number of protons is going to equal to 1. Now, how did I get that 1? It's not really because of this right here. It's because anytime I'm given the element identity, hydrogen in this case, I can actually look at a periodic table, which I'll do right now, and see that hydrogen has a 1 right there. Right? That's your atomic number. So then, when we look at this right here, we know that the number of protons is equal to 1. How about the number of neutrons? Well, the number of neutrons, I don't know just quite yet. But again, I'm given some clues here because the mass number is equal to 1. So if my mass number is equal to 1, and I know the mass number is protons plus neutrons, well, that means the only way for this to work out is I have 0 neutrons. What about the second one, hydrogen 2? Hydrogen 2, in this case, right, I'm going to scooch this one down here. So for hydrogen 2, how many protons do I have? So again, going back to the same logic as before, I only have 1 proton. Hydrogen, right, as an identity, is known to only have 1 proton in all atoms. What about the number of neutrons? Well, the number of neutrons, again, I still don't know just immediately quite yet, but remember that 2, this number afterwards, that's your mass number. That mass number is the sum of protons plus neutrons. So if protons is 1, neutrons I don't know yet, 1 plus what will give me 2? It's going to be 1. So that's 1 proton and 1 neutron. You can see the other examples work out that way. You can kind of figure them out. Just for the sake of comparison, helium-3, for example. Helium-3, well, the number of protons in this case is going to end up being 2. Where did I get the 2 from? The 2 comes from the periodic table, knowing that helium has an atomic number of 2. I know that the number of protons is also 2. So P equals 2. That means for this specific isotope, the number of neutrons, right, since the sum of protons and neutrons is 3, that means my number of neutrons has to be 1. How does that get translated then into a nuclear symbol? So switch this over to the right side. So you have these nuclear symbols. You have H in the middle, which you can probably surmise is the symbol, and you have the 1 and the 1. Down here you have a 2 and a 1, 3 and the 1. Well, what do you notice? Well, again, it's pretty convenient here, is that this 1 is very much the same thing as the mass number, right? This 2 right here comes from the mass number. This 3 on top comes from the mass number. What about the numbers on the bottom? Well, those come from the atomic number, 1, 1, 1. They're all the same element, so you have 1, 1, 1 there. Whereas in helium, right, you have 2 and 2 on the bottom, but the top is 3 and 4. Where do those come from? Those have been designated as helium-3 and helium-4. So you can go through and basically figure this out using some of these arrangements and how we designate isotopes. So for this, it's asking you to determine the total number of protons, neutrons, and electrons for neutral atoms with the following isotopes. Right, so scandium-46 is our first one. Scandium, the element, is going to have a certain number of protons. How do I know that? Well, because scandium will always have the same number of protons. I'm going to scooch back over here. Scandium is Sc. That's number 21, the atomic number there. So that's going to be 21 protons. How about the number of neutrons? Well, I don't know that because I kind of have to do a little bit of math. I'm given some information about it right here. Right now, the answer isn't 46. Remember, this is the sum of protons and neutrons. So doing a little bit of math here. Hopefully you can do the math to figure out that this is going to end up being 25, right? Because 21 plus 25 gives you 46. So the number of neutrons is 25. Got to do a little bit of work to get there. Finally, the number of electrons. Well, a lot of times, since this is going to be a neutral atom, but a lot of times it's kind of convenient since positive protons have a charge of 21 total positive things. That means you have to have a total of 21 negative things to counteract that. So there you go. Try the other two. It's very similar setup. In this case, instead of being given the hyphen notation, you're given the nuclear symbol. Now, how exactly does that apply here? So let's see how this works with atomic masses. First of all, note that this first definition here, that absolute atomic mass, this is an impractical sort of value to work with. So this is basically if you took one single atom and put it on a balance, what is that mass? It's a very, very small amount. So the absolute atomic mass of oxygen-16, for example, is 260 or 2.657 times 10 to the minus 23 grams. Yes, that's a actual mass, and it's really difficult to work with numbers like that, so we don't actually use that at all. Instead, what we do is we agree upon, and this is the scientific community, one standard isotope to compare all other isotopes. Carbon-12. Now this picture of Beyonce here, of course, why is that there? Well, she's kind of like the standard for a lot of people of what a most wonderful artist and sort of celebrity and somebody who kind of is being compared to, right? Everyone compares themselves to Beyonce to a certain degree. So in this case, carbon-12 is our Beyonce. Carbon-12, specifically this isotope, carbon-12. Now let's kind of break that one down a little bit more. Carbon-12, I know that it has 6 protons because it's the element carbon, and its atomic number is 6, right? It's the 6th element on the periodic table. And the number of neutrons also ends up being 6 because 6 plus some unknown number equals 12. Well, it's got to be 6. So the number of neutrons is also 6. So 6 proton, 6 neutron atom, this carbon-12. This is going to be defined as exactly 12 atomic mass units. It's kind of further defined here. So 12 atomic mass units, that means 1 atomic mass unit, or AMU, is the mass that is exactly 1/12 the mass of carbon-12, right? We're comparing it to specifically carbon-12. Whereas the relative atomic mass, this is where it gets a little bit tricky, is the mass of some atom as it's compared to carbon-12. So if I know that carbon-12 has exactly 12, that means if I compare everything else to this carbon-12, that is a relative atomic mass. It's being compared, right? Relative is referring to being compared. Let's kind of see a little bit in terms of what that means. So over here, here's some examples of atomic masses. I've got 3 columns here. I've got the specific isotope, all these in hyphen notation. I've got the absolute atomic mass, which is what it would be if you put this on a balance. And then with the relative atomic mass, which is when you compare it to carbon-12. So this first one, carbon-12, it's got some mass here, yada, yada, yada. The important thing, though, is that it is exactly 12 AMU. This is the gold star standard. What about hydrogen-1? Well, again, it has a mass of an individual atom, but also it has some AMU. So they basically did some sciencey stuff, basically, and took some hydrogen atoms and then compared it to carbon-12 so that it ends up that atoms of hydrogen-1, where you have just 1 proton and no neutrons, this kind of atom actually only has an AMU of 1.007825. Right, what about carbon-13? So carbon-13, as a comparison, right, that's going to have 6 protons, and it's going to have 7 neutrons, right, because 6 plus 7 equals 13. That's very similar to carbon-12, right? It has 1 more neutron than carbon-12. So in this case, its relative atomic mass, right, the mass of carbon-13, when compared to carbon-12, is going to be 13 point yada, yada, yada. Now, obviously, you're not going to have to know this stuff. This is just a general comparison. But as you see in this last one right here, again, this is going to have a proton count of 5. It's going to have 7 neutrons. And then you can see that the AMU is pretty close. It's not exactly 12, but it's 12.01 something. Because again, that value is generated by comparing it to the exactly 12. How that works is not super important. Just know that these values are a ratio that's generated by comparing it to 12 AMU. So what exactly does this do in terms of atomic masses for what we can use? Well, atomic mass as a broad concept, of course, has a couple types. We've already talked about absolute atomic mass. We've talked about a relative atomic mass. In this case, atomic masses for elements are actually defined, of course, as a comparison to this isotope carbon-12, our Beyonce there. So then if you look at the periodic table, you have 12.011. Why is this atomic mass on the periodic table not just 12? Why is it 12.011? Why are there decimals here when we decided earlier that it's exactly 12? Well, remember that this doesn't say carbon-12 specifically. It just says carbon generically. And remember, there's not only one type of carbon. There's many types of carbon. There's many isotopes of carbon. So the answer, of course, is that because you have different isotopes, kind of like what we saw up here. So this is one isotope of carbon. That's another isotope of carbon. It's still carbon. Because those exist naturally in the world, they each contribute to this mass. So it's actually an average. The 12.011 is an average of the different isotopes of carbon. So to kind of put this into context, we need to apply this idea of something called a weighted average, What this is, weighted average is, what this average atomic mass, is that it's a weighted average of the relative atomic masses, right? So there's kind of lists of something AMU, of the naturally occurring isotopes of an element, a single element. All right, let's talk about what a weighted average is first. So this little subsection here specifically refers to this definition. What's a weighted average? So there's a box of marbles, contains its two sizes. 25% of the marbles have a mass of 2 grams, so maybe these smaller blue ones. The 75% of the marbles, these bigger yellow, red ones, have a mass of 3 grams. So what's the weighted average of the marbles in the box? So I hope you kind of recognize here that I can't just take an average simply by taking 2 plus 3, dividing it by 2, because there are different numbers of each of them. There's a lot more of the heavier ones, a lot less of the smaller, lighter marbles. So I can't really just, again, take a simple arithmetic average. Instead, I'm going to do a weighted average, which takes into account that relative percent of each type, so whatever is there. So in this case, this is going to be a value where I take 2.00 grams, which is the mass of the smaller one. I'm going to multiply it by a 0.25, which is the decimal form of the percentage, which is the more useful one. And I'm going to add that then to the 3.00 grams times the 0.75% that corresponds with the larger marble. So what this does again is it allows us to account for that relative percent of each type of marble in this box. And the result of this will get you what the average is supposed to be. Numerically, this ends up being 2.75 grams. So that's the average mass of the marbles inside that box. Now, it's kind of weird, right? You can think of average as just being like adding two things and dividing it. But of course, when we talk about the different amounts, right, the different percentages that exist inside the box, it's not that simple anymore. Effectively, if you look at it, it's just basically 2 times this plus 3 times this, and then whatever comes out is the average mass. So going back to average atomic masses, right? This is the application of it on this page. So how do we calculate it using some given information? So the average atomic mass, right? This is what we actually see on the periodic table. The average atomic mass depends on 2 parts. The relative atomic mass of each naturally occurring isotope, right? So there's that substance, that number that comes from being compared to carbon-12. And then the relative abundance of each isotope. Let's see how they appear down here. Let's talk about the relative abundance, which means this relative abundance for this is in this column. Now, what exactly does that apply to? Well, it's saying that there's 2 isotopes here of copper, copper 63, copper 65. These are given to you. Just know that that's information that's available to you. And know that in the world that exists, 69.15% of it is copper 63, 30.85% of it is copper 65. Right? Remember that these are the labels of copper 63 and copper 65. Tell us what the isotopes are, and the relative abundance tells us what percentage of the world that has copper is made of this specific isotope. And then you also have the atomic mass. Now this chart doesn't have this specific word, but really again, these are the relative atomic masses of copper 63 and copper 65. So these 2 numbers, again, at some point, somehow, some way, some scientists compared it to carbon-12 and determined that it's going to have 62.929601 AMU. So how do we do this, right? So just like before, the average atomic mass is a weighted average, just like we saw before. We can't just stick numbers in and divide it by 2, right? You can't just take the atomic mass and the atomic mass here and then divide those, take the sum anyway and divide by 2. That's not how this works. You have to incorporate the relative abundance. So it's pretty straightforward. Let's go ahead and write this out. The average atomic mass, there's not really a symbol that we're going to use here. We're just going to write the word out. Average atomic mass is equal to the relative atomic mass of an isotope times the relative abundance of the isotope. So it's going to be 62.929601 AMU times, and this, right, 69.15, got to convert it into a decimal form, 0.6915. So that's that first point. And then you add it to the atomic mass of copper 65, 64.927794 AMU times 0.3085. And that's all the setup you have to do here, right? So you're going to take each isotope and multiply the relative atomic mass given to you here, multiply by the relative abundance, and then add it all up. Of course, we're going to do this according to the rules of significant figures. So let's do this step by step. With these two are going to be multiplied, and then we get out some numbers. So the result of these, again, I'm going to multiply these together and then round. I'm going to multiply these two together and then round, because those have their own rules. That should give you a result here of 63.55 AMU. All right, so let's talk about kind of what this means. If you look here, right, this copper 63, copper 65, remember these are not involved in these calculations. These are solely labels for the isotopes of copper that they are. You only use the relative atomic mass, not the mass numbers, right? The relative atomic mass. And then, of course, the relative abundances are provided here. You set it up, you work it out, and you get 63.55 AMU. Now, how do we know that we're at least on the right track with this? Well, if you scooch over back to a periodic table, let's find copper. So if you find copper, which is right here, right, what do you see here? Well, that number on the bottom is 63.546. Well, that's about the ballpark value of what we just calculated, 63.55. So that number, again, is the result of this weighted average calculation. This value is the average atomic mass, which we used by applying the weighted average to the relative atomic mass and the relative abundance. Finally, to kind of wrap up a few thoughts here, when it comes to language, atomic mass, generally speaking, you hear it a lot, could refer to the absolute, relative, or average atomic mass. Usually, it means the average atomic mass. So kind of from here on out, unless it's specified, usually assume it's the average atomic mass. So whatever this number is down here on the bottom. If it's asking you specifically for an absolute or relative atomic mass, those have its slightly different definitions, so apply those appropriately. So as an example, what is the atomic mass for oxygen? So sometimes you'll just hear that just out of the blue. So what that's saying is, what is the average atomic mass for oxygen? And so by looking at this value down here at the bottom, you know that's going to be 15.9994 AMU. Another annoying thing is this distinction between atomic weight versus atomic mass. Atomic weight, that's again just kind of one of those old words that's stuck around for a long time. Hasn't quite really left yet. So average atomic weight, if you hear that, is the same thing as the average atomic mass. All right. And to wrap up this, just making sure that we can round from the periodic table. You have probably noticed that some of these numbers are pretty long on the bottom of the periodic table. So we're going to kind of come up with a system for simplifying a little bit. You have the option here, or not the option, but you need to go through two things to check. Anytime you want to take a periodic table atomic mass, you should round to at least 2 decimal places or 4 sig figs, whichever one gives you more. It's 4 significant digits, 4 significant figures. So, for example, right here, oxygen, this one's going to be 15.9994. So the question is, do I use 2 decimal places or do I take 4 significant digits? Well, let's figure out which one gives you more. If it's 2 decimal places, it becomes 15.99, right? That 9 gets rounded. So actually this one ends up kind of rounding up to 16.00. All right, that's for 2 decimal places. What about 4 significant digits? Well, it turns out it rounds to the same place, so you would still get 16.00, right? 15.99, the fourth significant figure. You round there, so it ends up being the same value. So luckily for oxygen, the same value is appropriate. What about bismuth? All right, let's see it. 2 decimal places for bismuth will be 208.98 AMU. 4 significant figures is 208.9. We'll have to round that, so that becomes actually 209.0 AMU. Whichever one gives you more digits to work with is the one you want to keep. So between 208.98, 209.0 AMU, which one do you want to keep? Let's keep this one. Right, so that's the one you'd want to use. So in this case, 2 decimal places gives you more than 4 significant figures. Whereas in oxygen, 1616, right? They both give you the same value, so you can use either one. Finally here, just as a quick note, some atomic masses are written in parentheses, right, or in some sort of brackets, signifying that there's no stable isotope. So whatever isotopes do exist, they typically decay radioactively, and then it's really difficult to actually observe a mass. A lot of times you might just see it as like a 257. Sometimes it'll provide value, sometimes not. That's what that parentheses means. Finally, the terminology here, this is just a summary of all the terms that we've seen so far. It's going to be up to you to kind of keep track of them and to know what the differences are. They sound very similar, right? If you look at this, the word atomic shows up in like 4 or 5 of them. The word mass shows up in 4 or 5 of them, but they all have slight different meanings. All right, that'll do it.